I can move my stuff too. It's okay. You, that one's between me and Run. That's Run's backpack. Okay, so.
Good. That's all right. Oh, okay, this is good. All right.
Are you already downloaded?
Yes.
Where are they?
So if you go down to the bottom right.
Yeah.
you'll see all the presentations are.
And Maria is online. She will share her screen. Oh, great. So we just opened them. That's great. So are you? Maria is online. She will be sharing her screen.
Yes.
So please.
Theoretically.
Oh, no, some are. Yeah, 3 years. I was gonna submit it to you, but I don't know, but,
We are still.
I'm gonna need some stop sharing Wednesday, Friday sometime. But I said, hey.
They're fast. If you need any help, my colleague Paul and I will be able to.
Scheduled stuff. Last minute people drop meetings. No, anyway, so timer for everybody. Yeah. Welcome. It's the second day of our working group winter meeting. Welcome here in the room and online. We are excited to have some speaker this morning. The agenda was there, but now it disappeared. Maybe I can get that back. Here we go. So this morning we'll mostly focus on the chemistry and the WACM and high altitude developments for CMIP 6. There will be a few talks, as you can see. One is remote first. And after that, we will have a discussion and a break. And at 11 o'clock, there's then a seminar in this room. You're all welcome to join. And then, of course, we resume later, again after lunch with the afternoon session. Okay, I don't think there's anything else we need to announce. So we'll see if we can already start. Maria, are you online?
I am. Can you hear me?
Yes.
Okay, I can hear you, so fine. So I was told that you were going to put my presentation there.
Oh, you want me to do your presentation?
That's what I was told, that it was going to be on the multimedia.
Yeah, but you
view.
can also share, but that's fine. I'm happy to do
okay.
that.
No, okay,
I think
sorry
she can
about
share,
that.
right? Yeah.
So
Why don't
the
you
other
go
thing is
ahead
that,
and share?
shall I share? Okay, perfect then. The other thing is that I'm with Firefox. I didn't plan that. So Firefox and Google Meet doesn't work really well with my, okay. There is Joy Ehrman that is currently presenting now. Is the main presenter in Google, in my Google Meet. Yeah, at the Google Meet, somebody is presenting. It says there is Joy Ehrman, so I cannot.
Okay, I stop presenting. Now try.
Okay, so I go ahead now and present. Let's see.
Is it
So, do you see it now?
No,
No?
we don't see it. Not yet.
No, it's okay. Let me see, because now I lost.
You know what? It's fine. I can
Then,
present
yeah.
it. So
Is it okay? Because I always have problems with Firefox, and I understood that the presentation was going to be on the multimedia queue, so I assumed that you guys were going to put up the presentation on the screen. So the only thing is that people online won't be able to see it, right, Simone?
Yeah, they'll see. Okay.
Oh, they will see it. Okay.
Oh, I'll just then advance your slides.
Okay.
Yeah. Okay. Thank you.
So are you all right if I say next?
Yes.
Sorry about that. Okay,
so our first speaker is Maria Van Matten from the University of Sheffield with the title Soil NOx Emissions and CSM2 Implications for Atmosphere Chemistry. Please start.
Okay. Thank you so much. So yes, as Simone said, I'm at the University of Sheffield and I work at the Leverhulme Center for Climate Change Mitigation. And before I start talking about soil NOx in CSM, I would like to say thank you to many people that has been involved in this work, as well as the UKRI and the Leverhulme Trust for funding. So next. So this is just a diagram that shows really in a simple way how the nitrogen cycling in CLM5 works. It's called the holes in a pipe concept. So it means that nitrogen inputs come in, nitrogen output comes out. And some of the nitrogen inputs are nitrogen deposition, fertilizer, or nitrogen from the organic matter. Some of the outputs are the nitrogen uptaken by the plants, nitrogen loss from leaching and runoff, and then also N2O emitted from nitrification processes and N2O from denitrification processes. And all these processes are being controlled by environmental conditions as well as the soil properties. So this is what we have in CLM5 now. So next, as a part of the Leverhulme Center, sorry, I have a little bit of animations in this slide, but as a part of the Leverhulme Center, we have done some implementations on the nitrogen cycling. So we added ammonia from volatilization, and that was done by the Amos Tai's group at the Chinese University of Hong Kong. Next, Simon. We added nitric oxide from denitrification and denitrification. And next, and soil pH, because the default scheme has all the nitrogen cycling considering a default soil pH of 6.5. So we added the soil pH. So all these implementations have been well documented. Simone, next, please. So it has been documented in 2 articles. And so today what I really want to focus on is on the soil nitric oxide scheme. So next, Simone, twice, give it one more. So we just go ahead. So this is my only equation today. So, and is the soil nitrogen oxide equation that is based on the Parton et al. 2001. So it comes from the Dyson biogeochemical model. And so it has a canopy reduction factor. So that means that not all the soil nitric oxide emitted by the soil reaches the atmosphere, and also has rain pulses in the nitrification process. So you can see that it's really depending on N2O. So it has a ratio that depending on the environmental conditions and the soil process, the soil properties determines how much or what is the fraction of the N2O that is emitted in the nitrification and nitrification that will emit nitric oxide. So next, Simone. So we, in the Leverhulme Center, we were focusing on agroecosystems. So we did a really thorough evaluation of the model on the soil agriculture emissions. We started with N2O. So overall, CLM5 was capturing reasonably well the N2O emissions. We used field observations at the energy farm, which is a field, it's a site at Illinois, right at the core belt. And we also use N2O monthly estimates from Cindy Nevison's work, which is an inversion, is based from an inverse modeling analysis approach. So you can see that actually CLM5 picks really well the seasonality and the magnitude, especially during the summertime from the agriculture emissions in the core belt. We also identify several emissions inventories that we could use to do a more global scale comparison, and we focus on 5 major agriculture regions. We use EDGAR and ENMIP emissions inventory or data, which ENMIP is the N2O multi-modeling intercomparison project where 10 land models participated, and you can see that CLM5 reproduced well the seasonality and the magnitude. Of course, we have to recognize, and you can see that in the scheme, that there are in these plots, there is a wide variability as well among the different scenarios, the different emissions estimates. So next, so we also look at the soil agriculture NOx emissions, and in this case, we were able to identify more emissions inventory. And we can see that actually CLM5 reproduces well as well, again, the seasonality and the magnitude of the nitric oxide emissions from croplands. And again, you can see that there is a wide range of estimates in the emissions inventories available. Next, Simone, I think you can do twice. One more. Okay, there we go. So we look at also the global annual estimates, and we compile a series of estimates available in the literature. For N2O, we can see that CLM5 is within the range of previous estimates, and I'm highlighting there as well the MIP annual value. For soil nitric oxide, we can see that actually soil nitric, the total global estimate in CLM5 is in the lower bound. I mean, it's within the previous estimate, but it's in the lower bound. I have also highlighted here HEMCO because it's the tool that is providing emissions estimates to atmospheric chemical transport models as CAM-CHEM, and we have been talking about HEMCO quite a bit in this past meetings. So next, Simone, please. So I wanted to give you an example of why it's important to consider a soil NOx or a dynamic soil NOx scheme within an air system model. Within the Leverhulme Center, we work with enhanced rock weathering. This is a land-based carbon dioxide removal strategy that consists of spreading volcanic rocks on field croplands. So volcanic rocks is like basalt, these rocks that contain silicate. So these rocks, crushed rocks, are able to react with carbon dioxide from the atmosphere, and they form cations and carbonates and bicarbonates that eventually are washed down into the ocean and stored as sediments for more than 10,000 years. So this is just a really simple way to explain what enhanced rock weathering is. But next, so within the Leverhulme Center, we have field sites across the world, from the energy farm at the Illinois, all the way to sugarcane plantations at the in northern Australia. So we not only look at the potential of the carbon dioxide removal of this strategy, but also what are the indirect feedbacks that can happen in the soil from spreading basalt at a large scale. So next, Simone. So one of the things that we have been looking at, especially our colleagues at Illinois, is the effect of the soil N2O emissions from basalt applications. And in this figure on the right, on the left, you can see cumulative N2O fluxes. You can see that the basalt, which is the black solid dots, have in 2017, there is a lower N2O fluxes compared to the control plots. And this one was linked to an increase in soil pH. This is an example for 2017, but we have been doing these field trials since then. So every year we have consistent results, the same results, and not only in corn plots, but also in soybean and miscanthus, which is a bioenergy crop. So a decrease in N2O emissions will actually produce, don't worry, Simon, keep going. Sorry. So since nitric oxide emissions are really linked on the N2O emissions, not directly, but there is, we are expecting that a decrease in soil, the effect on soil pH will also affect nitric oxide emissions. So we have a paper currently under review now where we have done a modeling study to see how enhanced rock weathering could help the US reach net zero by 2050. So I don't want to go into detail about the CDR estimates that we had, but what I wanted to focus on the results that we had for the nitrogen cycling. So I have here on the right the soil NOx emissions from CLM5 present day, and then the decrease in soil nitric oxide by 2050 if we would apply basalt across agriculture regions in the UK, of agriculture fields in the UK, in the US, to actually reduce, to sequester 2 gigatons of carbon dioxide per year. So we can see that there is an important decrease, and soil nitric oxide is about 20%. So what we did is that we put the soil nitric oxide within CSM2. Next, thank you. And to look at the effect on air quality on surface ozone. So in this case, we were focusing on the MDA and the AOT40, which are the air quality standards to protect human health and crop damage or crop health. So you can see that actually this 20% decrease in soil nitric oxide emissions just from agriculture in the US in 2050 have important consequences for surface ozone. So since the Leverhulme Center, we focus on agroecosystems, we were also interested to see what would be the indirect effect on the crop yields. So we use the AOT40 to estimate the avoided crop damage on corn and soybean. So it's not a significant increase on the crop yields from this indirect effect from decreasing surface ozone, but we are seeing a 3% and 4% increase in corn and soybean. And if we put that into economic values, actually, farmers would be able to have an economic benefit of $200 to $500 million per year. I think this is next. So this is my last slide. So I just wanted to highlight actually how important it is to consider dynamic soil NOx schemes within Earth system models. Right now, CSM2 has a fixed amount or fixed emissions in 2000, I think, or 2010 from Edgar, which are really great to get by the background nitrogen oxides concentrations or mixing ratios, but I think it's important to consider how soil nitrogen oxides might evolve due to climate or to land use, land cover changes. So the soil NOx scheme is being implemented in CTSM and will be released within CSM2. And Simon, correct me if I'm wrong. There is a ticket, so it's work in progress. And of course, there is room to validate the scheme further and also to improve it. So I'll be happy to collaborate or to talk to the community if somebody will be interested in taking over and using the scheme as well. Thank you. I take questions now.
Thank you. Hey, other questions? I do have a quick question already. So when you implement this for present day, do you see any changes in the atmospheric response? Do you see changes in atmospheric NOx and therefore ozone? Because you nicely showed the effects when you apply this climate intervention.
So I don't think I have done a test where I just kept the soil NOx emissions as default by the model. So what I did for this study is that I ran present day with the soil NOx from CLM5 and 2050.
Yeah.
So yes, I haven't looked at, but I mean, we are looking at this effect on surface ozone, and there might be also effects on other species as well, on methane lifetime or OH. I mean, that would be a really interesting thing to test, actually.
Yeah, that would be great. Other questions, Dave?
Well,
I don't know who was first.
Yeah, so thanks, Maria. This is Dave. So you showed some agreement with the observation of the model, although looking at those curves, you said good agreement. It looked like, to me, there was, you could argue, well, the observations didn't agree with each other in most cases, and then the model is also different. So let's, be cautious, I guess, in saying that the model's doing good. But I'm curious if you have a sense of how sensitive the results are to like the amount of fertilizer that's being applied versus soil nitrogen processes versus sort of just standard crop processes, which are determining how well the crops are growing in different parts of the world. And particularly knowing that we have like a big problem in India in CSM2, which is a big agricultural region.
Yeah, I haven't tested that. So I would just focus on the changes in soil pH because from basal application. So I did that sensitivity test with soil pH, but I didn't do a sensitivity test changing the fertilizer applications. I think this is this is something that we should look at as well. The other thing is that for the soil NOx scheme that we are implemented now in CTSM is independent on the soil pH. So it's just like the simple version of the first implementation that I did.
Okay. Mary?
Yeah, nice talking, Maria. I'm curious, as we go to more simulations with regional refinement, if you expect any challenges with the soil NOx implementation and, or, what might you expect with the results changing?
So I have run the CLM5 at 50 by 50 kilometers and as well as 100 by 100 kilometer resolution. So in terms of the land model, I didn't see any major changes in terms of the spatial distribution or the overall flux. That will be really interesting if we just go through Musica, for example, and we couple the model into a more refined actually system than running it with CSM2 at 100 by 100 kilometer.
And
So I think,
are any of the data sets resolution limited or it looks like it's good to go?
so what do you, didn't
I assume
understand,
that there are
sorry,
data sets to help you with
with the,
the emissions. Got it.
so with the emissions, I have emissions at 50 kilometers and as well as 100 kilometer resolution. But what we are doing now is that we have Musica framework over the UK. So we are trying to run the soil nitric oxide emissions over the UK at really high resolution. So we are dealing right now with the downscaling the emissions. So this is work in progress actually. So that will be really interesting to see how that will affect on a high resolution.
Definitely, thanks.
Okay, I think, thank you, Maria. Great.
Welcome. Thank you for having me. Bye.
So our next speaker is Danny. I'll put it on slideshow. Thank you. You can manage that. And so, is that the first? Yeah. So Danny is ASP at ACOM, working with us and is talking about a historical dust emission data set for better evaluating aerosol radiated forcings.
This is no.
Oh, this is the wrong one.
Yeah.
I just saw your name. Good. We do that this afternoon. He's actually giving 2 talks. So wait, we need to stop this here. There we go. Let's see if we find your other one. Is there another one? Maybe they did not upload the right talk. There it is. This is the right one? Yeah, this is the right one. Good, I read the title, so we are in the right role, but we're good. We're good. Okay, for now, we first listen to the first talk, which is I was kind of wondering why that title was. A new mechanistic dust emission scheme. That's why we're here today, this morning. Go ahead.
Right, thank you. Yeah, I know the title slide looks the same, so I was just too lazy to change the picture. So anyway, bear with me. Yeah, so yeah, I'm talking about a new mechanistic dust emission scheme today. Some of you may have heard it a few times already, but I'm just giving some updates in the testing and tunings in CSM2 as it goes into CSM3. So I just want to acknowledge my collaborators, Jasper Cook at UCLA, Lorelei and Natalie Mahol at Cornell, and then my anchor mentors and collaborators, Dave Lawrence, Simona Timmers, and Eric Luzek for their help in their work, and also other European collaborators. So the motivation is basically CSM. We care about air quality predictions, and thus it's a potent air pollutant. So we care about predictions in models, and basically CSM does not do so well in capturing the variability. If you look at left-hand side modus archon, right-hand side sender or dead dust emission scheme in CSM22, you see several big blobs across the globe, like over Sudan, China, Australia. That's not being appearing in the left-hand side in the satellite product. So we thought dust sources are wrongly located, and we thought new emission physics or schemes would be able to help highlight the right source locations across the globe. That's the motivation. I'm just going through the configuration a little bit. We're using FHIS, so it's a transient land atmosphere coupled node chemistry for now. We're using CTSM, SPMO, satellite technology, CAM6 with MEM4. We're going to talk about MEM5 a little bit in the last slide because that's default in CSM3. We're using FV dicole for now with nudging toward mirror 2. We'll also talk about SEC SLAM in the last slide for CSM3. We'll talk about, we're using a 1 degree resolution, half an hour time step, and 5 year simulation, 1 year spin up in this study. And so just to note that most modifications of the dust emission process are in the land model. So because that's where the dust emission scheme is. So we are just modifying in CTSM5, and then we are evaluating how dust distribute across the globe in CAM6. Just giving you 2 examples of current existing dust emission scheme sender, which is used in CESM, and then Code 2014. That's our base scheme. We chose to base our new developments on top of Code 2014, although it can also be based on top of sender as well. And I just want to say that dust emission scheme is a threshold parameterization. So you see something like this, dust emission flux and mass flux could be greater than 0 when the wind speed or the used friction velocity is greater than a certain threshold value. And that threshold value is increasing with soil moisture content. So dust emission flux, the behavior or the variability is dictated by these 2 variables mostly. And then another thing is we choose to tune global dust emissions to a certain value where we can yield a global mean dust AOD from CAM6 to a value of 0.03. This is a global constraint provided by David Ridley and Colette Hill. It's a good global dust constraint for the year 2000s. Here I'm talking about 2 additional considerations. Again, they can be added on top of different dust emission schemes. We are just choosing Code 2014 for our base scheme. 2 stories here, a summary of them. So the first one is the wind momentum partition by rocks and plants. We have U star that represents wind momentum for soil erosion and dust emission. Not all of them will go directly into the soil because there will be surface obstacles like rocks, plants, pebbles, boulders, and so on and so forth that protect the soil from being eroded. So we need to account for surface obstacles that partition the momentum. So dust modelers a few decades ago, they came up with a parameterization that calculates the fraction of the wind momentum that goes into the wind erosion and dust emission. So it's a factor that goes from 0 to 1. If you look at the Sahara, for example, the most erodible source regions like the Baudelaire Depression and El Jouf and the Arabian Desert in Saudi Arabia, for example, you'll see they have values close to 1. That means almost 100% of the momentum goes to dust emissions and soil erosion. If you move further away to rainforest, for example, values drop to 0, meaning there is very little wind momentum that's being able to be used for wind erosion and dust emission. So the factor here is dependent in our scheme on the roughness length of rocks and LAI as vegetation roughness, and we are going to multiply this factor by the U star to scale U star up and down in the dust emission scheme. So hopefully we can use this implementation to highlight the main dust sources across the globe because that's what we highlighted for U star here. We have close to 100% of momentum going to dust emission. So hopefully we can highlight the main dust sources across the globe. The second story is the sub-time-step wind fluctuations. You know that CSM has really high time step, like a large time step of half an hour in CSM2, and it's not resolving the sub-time step high frequency wind fluctuations of periods of less than a minute or so. So the dust emission schemes they are just using a mean time step mean wind and then evaluate the dust emission flux. So that's what most dust emission models, current dust emission models are doing. It's the black line showing here. Within a time step is either 100% of emissions if the time step mean wind is greater than the threshold range or it's smaller it's 0 if it's smaller than the threshold range. And that's exactly what our scheme wants to improve, is to be able to capture those gusts and episodes within a time step that's able to sweep across the threshold and generate some small occasional intermittent emissions within that time step. So that's what we are showing here is our scheme in this scatter plot. We're able to capture some gusts and episodes using a statistical parameterization. Of course, we're not explicitly resolving the turbulence and the turbulent wind fluctuations, but we are able to capture some small intermittent emissions within a time step. And that's really important for certain regions like the marginal source regions and, like the high latitude polar deserts. If you look at Canada and Russia, for example, you see we'll be able to reproduce like 20%, 30% of intermittent emissions within a time step if you average across the whole year. They usually have really high dust emission threshold and nearly 0 dust emissions. That's what Sender and Co won't be able to produce. But we're able to produce high latitude dust emissions over the polar deserts in Canada, for example. So that's what we thought is important to reproduce because we are observing them in the field campaigns. So we come up with this fraction of time eta as a scaling factor. We're multiplying it into by the dust emission flux to scale it up and down. Eta is a statistical parameterization capturing the statistical behavior of the fluctuations. So we're using the mean U star, the U star for the whole time step, and also the fluctuations parameterized by the similarity theory. And of course, we also need to know the dust emission threshold as well. So hopefully it will be able to enable us to capture the semi-arid and high latitude emissions. Okay, so quickly going through the evaluations in CSM, this is our scheme. So hopefully it's now highlighting the major sources like the Beaudelet Depression and El Juf and the Arabian deserts better than Sender if you compare against Modus Aqua products. And at the same time, we are able to capture some high latitude dust emissions in our scheme, which is not appearing in Sender's scheme. David Ridley and CollectView, they have regional dust AOD values optimized. They are good for model evaluation. So we are separating dust AOD into 15 regions, 4 seasons, and you can see Modus Aqua highly consistent with their regional values. Our scheme does a very decent job as well. Sender does a decent job as well. It's not just as good as our current scheme. We also have in situ site observations of dust PM concentration and dust deposition fluxes. And the point here is basically showing our scheme does a better job matching against those site observations. We also have computed daily correlation maps using Modus Aqua and our simulations. So you see Sender and our maps here, they look pretty similar. If you subtract the two, you'll see moderate improvements, especially over the dust belts. And that's what we think the best, the good source locations and source strings are really important in capturing the day-to-day variability of dust. This is just an example, I'm going to skip it. So lastly, going into CSM3, we're testing a little bit of our scheme's behavior in different model configurations. We're still using FK's no nudging in this case, but we are trying to test SE spectral element dipole, CESM grid, and MAN5 in these 2 additional simulations. So we are showing again FE MAN4 in the left-hand side. We have CESM in the middle panel. They look pretty much the same, right? Almost identical. No extra tuning is needed. Good news. MAN5, you have a much wider mode. So with a larger geometric standard deviation, so you have a lot more skewed mode, and you have bigger dust particles depositing faster. So in general, we have smaller global dust load here. You need to scale it up a little bit. You scale the dust emission up back here. So this is the bottom left plot here, just scaling up the dust emissions, giving the 0.03 global constraint. And then if you subtract the two, you see they look pretty similar, but if you subtract the two, you see MEM5 gives more concentrated dust focus over the source regions. Again, because they're just depositing faster, they are going less into the downwind regions like the Atlantic Ocean, for example. Lastly, I want to talk about the radiative effects. So I'm showing the short wave direct radiative effects and long wave direct radiative effects. On the left-hand side, we have some dust cooling blue colors here, reflecting, scattering sunlight back to space, and we have a little bit of long wave absorption, much smaller than the short wave cooling. So in general, the direct radiative effect is negative, so dust cools the climate. We have a little bit of positive cloud, shortwave cloud forcing by dust, but apologies for the color scale here. It's actually much smaller than the left-hand side, so it's overall comparable to the long wave warming. And then, so here, the last slide, take-home messages. We are expanding the dust emission scheme, including the momentum partition due to surface roughness and sometimes that wind using a statistical parameterization. And I just want to quickly go through a few points with asterisks. In CSM3, you can switch between learn and sender, thanks to Eric Klusak's work. We're moving the standard solid rollability map from CAM to CTSM in a separate PR, but we will, the dust tuning factor will stay in CAM. So people, CAM people can tune CTSM dust emissions in CAM. So again, we suggest tuning dust to a global mean of 0.03 following David Ridley and Colette Hughes constraint, no matter which dust emission scheme is used. For regional refinements, we suggest using the CESM tuning factor. If you want, if you just focus on a certain region, you can further tune it to minimize regional biases if you don't care about worsening other regions' biases. Although this is not highly recommended. So lastly, a lot of things will change in CSM3, so we'll just do continuous testing and tuning before the code freeze in the CSM3. Yeah, so that's it. Thank you.
Thank you. Questions?
Sure.
I'm curious about this, the enhancement for the sub-time step gustiness.
Yeah.
I'm curious what you think should happen when you reduce the time step of the model for configurations to use a shorter time step. Because on the one hand, you could argue there shouldn't be unresolved time, but on the other hand, the grid cells are rather large, so maybe there's some spatial variability in when gusts are occurring. Do you have any thoughts on that?
I'm not sure about what spatial variability you're talking about, but in terms of minimizing the time steps, it really comes down to whether CSM can resolve those high frequency fluctuations. So, you know, unless you're running something like LES, you know, no matter how small the time step you have in CSM, you won't likely be able to resolve those fluctuations. So the scheme will be still able to, you know, enable you to capture those statistical behavior because we're using the similarity theory following statistical parameterization. So even though you have a small time step like 4 minutes or even smaller in, for example, a regional refinement, we still suggest using this scheme. But if you have something like LES, then very likely the use of this scheme will be mitigated in the future.
Okay.
Yeah.
Okay, there's an online question by Chuck. Do you want to raise the question yourself? Oh, it's from Joey. Sorry, I did not see that.
Well, actually, it is for Danny. I missed the start of this presentation, and it's showing on my Zoom screen that Joey Ehrman was presenting. As a new resident of Arizona, I've observed that dust emissions in this area are strongly influenced by the degree of soil disturbance from human activities. Things like construction of homes are all around me, off-road vehicles, etc. Do you have any plans to include geographically based indices of human activities that generate such soil disturbances in future versions of your dust emission scheme?
Yeah, thank you for the question. That's our plan. We're thinking about how to do that. This scheme focuses on the natural emissions from the desert. So for human activities, land use, land cover change is not really well incorporated into the model. So we are looking into ways to parameterize it, but it still remains a challenge at this moment mostly because we don't have enough observations of how, like human land use, land cover change will interact with soil disturbance and dust emissions. Like it's really hard to separate the contributions from natural dust emissions and soil disturbance by human activity. So we do need to think about that. Hopefully we can include this in the future in the dust emission scheme.
Thank you.
Okay, thank you. Amy, let's
Right, thank you.
move on if there is no other questions. I don't see anybody. Okay, thanks so much. Great. Next is Louisa Evans. I'm all right, this is a PDF, so I think we just put somewhere on the screen. Okay, so our next talk is by Louisa Evans, and it's on the simpler chemistry mechanism for climate simulation, as we had talked yesterday. Thank you, Louisa.
Thanks. So these are really pretty preliminary results, but it's an attempt to provide a chemical mechanism that will be cheaper than TSMLT that we used during CMIP6, and still produce suitable ozone and oxidants to drive CAM. So just a little history about the Mozart family of chemical mechanisms. So we started with Mozart 1 in 1998. And as years go by and the computers become more popular, powerful, we realized we could add particularly more hydrocarbons to the scheme to more accurately represent ozone, particularly in populated urban regions. So Mozart 2 was published in 2003 and Mozart 4 in 2010. Mozart 3 side was stratospheric chemistry published by Doug at the same time as Mozart 4. And then T1 is what we've included in the TSMLT mechanism. So it really has quite a lot more hydrocarbons, particularly in the representation of aromatics and isoprene and terpene oxidation. But so I'm proposing that we could use something that we're calling Mozart Climate. In the past, I called this TS4, but we decided that was confusing. So this is very similar to the Mozart 2 mechanism. And this is also what Larry Horowitz has implemented in the GFDL AM4, but some comparable complexity. So this mechanism will be suitable really for CMIP type simulations and maybe hopefully for long chemistry climate simulations, but not really appropriate for some of the air quality studies we want to do. So in summary, TS1 had a total of 230 compounds, 42 of which were not transported. They were very short-lived radicals. Mozart Climate has 141 compounds with 15 not transported. So they both still, Mozart Climate still has the comprehensive stratospheric chemistry, which we really need in order to properly represent the ozone hole and other stratospheric chemistry that has an important influence for climate. They both have the full sulfur chemistry so that we can reproduce simulate eruptive volcanoes well. And then the Mozart Climate is really simpler chemistry for all the hydrocarbons that are larger than three carbon compounds. So So a quick comparison of some tropospheric budgets shows that they're really very similar. Same amount of total ozone, same amount of CO and methane. The methane lifetimes are essentially the same. And the aerosol burdens are also very similar. There's a slight change in sulfate, but all the other compounds are quite similar. So some quick plots of these results from the two simulations. So on the left is a zonal average of ozone for June, July, and August from the new climate chemistry simulation, and the difference from TS1 shows that over the seasonal average, there's less than 2 ppb difference in the troposphere. OH is also very similar. This is the actual concentration on the left in the climate simulation, and then the upper right is the absolute difference and the relative difference on the bottom. So you can ignore the relative difference where the concentrations are really low. So it's less than a 4% change in OH where there's some significant amounts. Here's the seasonal difference for sulfate. Even though there's some difference in the burdens on this seasonal average, there's really only there's less than a 5% decrease in sulfate from climate to the from TS1 in the climate simulation. And then I also did a longer run to compare the time series for these different compounds. So OH, so we can look at where these differences are. This is a zonal average at the surface for OH over these 10 years simulation. And so there's a slight, so on the left is the original TS1 mechanism, and on the right is the climate mechanism. So there's a slight decrease in OH, which is okay because our methane lifetime has been quite long. So I think this is fine. They look very similar in the mid-troposphere. And then the ozone zonal average on the bottom now is the surface amounts, zonal average at the surface, and then in the pre-troposphere above. And so there's a decrease in the surface ozone in the summer. These peaks are the surface ozone over the northern hemisphere in Europe that we generally overestimate in the model. So in the climate simulation, it's a bit lower. There are some more differences in the pre-troposphere, higher, a decrease in the northern hemisphere, but an increase in the southern hemisphere, but they're fairly small differences. And then also I looked at a few points to see how this is 40 north zonal average as a function of altitude. So we can see the stratosphere is essentially the same. And then this is at 20 south. And the zoom into those plots to look at the troposphere. There's a little bit more difference. As I mentioned before, the ozone's a bit lower in the northern hemisphere, but a little bit higher in the southern hemisphere, at least in the lower troposphere. So mechanism will be 30% cheaper. It's not a huge decrease, but hopefully this will help, especially as we go to more levels. These were preliminary tests. I've sort of been waiting for CAM to be frozen to redo these, but I'll do this very soon in a current tag, and so we can further verify it and make sure that this will be suitable for CESM 3 and CMIP 7 simulations. And that's all I have.
Yeah. For the summary, other questions?
So, I hate to add more species to your reduced mechanism, but, there's all these VSL, chlorine, and bromine, iodine species, and you probably could add on the order of half a dozen species and a few reactions to really enhance the UTLS chemistry in the model. It's time maybe to think about that.
Yeah, we really should do that. I think Peng will tell us this afternoon about, or is it tomorrow? Whenever. Yeah, one of the big differences we've seen between CAM-CHEM and the geochem simulations are the lack of halogen chemistry, as well as all our BSL work. So,
Yeah.
I think that's a very good point. We should do that.
Yeah, maybe just to add, and make sure people understand, that's really helpful when in the greenhouse gas chemistry then, right? If we would add those, we would get a better representation of the greenhouse gases and the forcing, is that correct? When we add the short-lived halogens, because they are climate gases.
Yeah, I think it's more ozone chemistry.
Okay.
and- But also, Alfonso Saez Lopez did a study and presented it last year at the working group meeting and showed that from pre-industrial to present day, there was a climate impact that was missing there. So
Right.
it's useful.
Another question? I saw Dave. And we do the online after Dave.
Well, let's go on one first, yeah.
Okay, who's there? Oh, Francis, please go ahead.
Yeah, you're 30% cheaper. Is that the solver itself, or is that ChemChem's 30% cheaper overall?
That was total overall CAM-CHEM.
Thanks.
But that was with an older 32 level. The difference should be the same because it's the number, primarily the number of transported species.
This is sort of a question for Maria and you and all the chemistry people. For the NOx emissions, if we go to the CLM updated NOx emissions, is everything in place to be able to like take those into the atmosphere and also presumably ignore whatever is coming from some other forcing data set, which must be treating the NOx emissions?
Yeah, we've had, in the past, we've just had a climatological emissions file that we've read in for soil and out. So that's easy to remove. And
So it's not combined with anything other than, any anthropogenic emissions or.
or it is, but we can.
It's separatable.
Yeah.
Okay.
Okay, Valerie?
Luisa, just freshman question. Can we expect that improvement in the tropospheric OH can be improve mesospheric OH predictions?
I did not look at the mesosphere. I doubt any of my changes have any impact on that. Sorry.
You want to go first?
Yeah,
Andy?
another question.
Yeah.
Okay, yeah, just to clarify, the MA and the TSMLT, are they just different configurations of Mozart or?
Yeah.
they're
Yeah,
differential?
I should have included them in here. So TSMLT uses all of this T1 chemistry and then adds on the stratosphere and then the Pugh mesosphere.
And the MA is.
And then MA doesn't include any of this. Middle atmosphere mechanism is only the stratosphere and it has methane for the troposphere. So it has sort of the blue and half of the yellow bars. So it doesn't have anything more than that. Yeah, I should have added this diagram. Dave.
Yeah, so this would be definitely the climate version would be what we'd use for the MT middle.
Middle top end.
Yeah,
Yeah.
middle top.
or low
And
top, middle top.
Would the same thing be used for Wacom or is
So
Wacom?
we'd have to add the chemistry for Wacom. That would, so all of these need the stratosphere added to them. Yeah,
So in general, maybe what would be really helpful would be have a figure that kind of like, it's like this one maybe, but then kind of goes through the configuration so that for those of us who can't quite keep all this straight.
right. Yes,
Especially me,
yeah, and CAM has just the sulfur chemistry and aerosols with specified oxidants.
I tried to yesterday present something similar, but you want really the information on.
Well, I like
Yeah,
this form, this
Yeah.
particular figure,
Yeah, I
helps
see
me
it.
understand a little bit about the complexity
Yeah, I
without
just
really
started-
knowing what's in each of these.
Yeah, I just started doing this for the troposphere. I'll make it.
Thanks. And Rafa, you have a quick question?
Yeah, sure. You show a really small impact on methane lifetime. I think it was from 7 to 6 point something. This is only with these 6-7 year simulations that you made. Did you make a longer simulation to see if this impact is larger?
Not yet. I'll do that. So,
Okay.
don't know yet.
Okay, thanks.
Right, thanks. Thank you. There are no more questions. Let's move on to the. Okay, let's find yours. All right. And I did it to
Where's the
you.
file?
You can just, yeah, this works. That thing should work too, but. I don't know.
Okay.
Yep.
Yeah, thank you. Yeah, today I'm going to talk a little bit about the status of our inline photolysis using TUVX or tropospheric ultraviolet visible model, radiated model. And I really want to highlight the work that the computer sciences have done on this project. Matt Dawson, Francis Fitt. The last 2 weeks have been pretty intense trying to get some results for this meeting. And then and Stacy Walters and Kyle Short has also done quite a bit of work. So today what I'm going to do is I'm going to talk a little bit about the two different approaches we've had for photolysis in our models. One is the lookup table approach, which dates back to the mid-2000s that I put together. And we've been using that for quite a while. It does not allow aerosols or clouds to be in the radiative transfer. So that's why we wanted to move on to an inline approach called TUVX, where that's allowed. And that's based on TUV 5.4, not 5 there. And Sasha Madronich and colleagues worked on that. So this is going to be a real simple talk. I'm going to start out and just compare the lookup table versus TUVX for the same radiative transfer, and just look for problems. And we did this, Matt and I, we went through all the different species and we found all kinds of issues, and we spent a lot of time correcting that. Then I'm going to talk about how these photolysis packages are used to calculate MLT heating rates, because this is also another very important thing that's necessary when you include high top models. And then finally, I'm going to show a 1-year run and just a couple figures that finished Saturday morning. And so you know, it is what it is, but it does give me encouragement to that we're on the right track. And then just a few conclusions here. So when you think about photolysis, this is the lookup table approach. If you look, let's see that, yeah. If you look like a photolysis rate like JO2, you have the exoatmospheric flux. Okay, that's given to you by an assessment. It's an 11-year solar cycle and as a function of wavelength. You have the normalized flux that we use, which is essentially the radiative transfer. It's a function of pressure and it's on pressure and wavelength grid. And then you also have the cross sections and quantum yields, which is dependent on the molecule you're interested in. And we broke that up in the lookup table approach for cases greater than 200 nanometers and less than 200 nanometers. We called it J short and J long. The greater than 200 nanometers was a lookup table, and short of 200 was inline photolysis rates for JO2 Lyman alpha, Schumann-Ruger band, JNO, etc. And then we we calculated the total J, and then we put a cloud correction factor on top of that. It was based on work back in the 80s from Sasha Madronich. We also calculate the heating rates all the way from 750 to 121 nanometers using the lookup table. And then at a certain altitude, we merged these heating rates with the CAM 6 heating rates of our RTMG. Now, TUVX is simpler. It's just you have one wavelength, 121 to 750 nanometers. You have everything in line. You have no lookup tables, nothing like that. It's more expensive, but it's a lot simpler and easier to maintain and update. So in here again, we do merge the RTMG with the photolysis heating rates around 60 kilometers, and instead of having a cloud correction at the end, what we do is we put the aerosol properties or cloud properties in the radiative transfer. And that's what we're working on right now. Now, in the process of, getting this thing ready for release in a couple months here, we had to go through all the chemical cross sections and quantum yields for every species in the model. And we started with the TSMLT mechanism, which has about 150 photochemical species. Not all of them are really sophisticated, but about 80 of them are pretty detailed. And when we did this, we noticed there were some problems with the temperature dependence because the inline TUVX really didn't worry that much about stratospheric chemistry. And so they didn't put a lot of the temperature dependence on halogens and things like that. So we had to go through and add all that in. And, there's one example on the right of what that looks like in JPL. And every species is a little bit different. You have to worry about the range of temperatures and the range of wavelengths that molecule is been measured in the laboratory for. So it's complicated. But we got there, we got through that, and we started doing some comparisons. And this is just a couple examples here. This is using the same radiative transfer. So we only want to look at the cross sections and quantum yields. So what we did is we ran in the same version of the model, one time step. And we took the radiative transfer for TUVX for both the cross-section quantum yields for the lookup table and the cross-section quantum yields derived from TUVX itself. And so the only difference in these plots would be a problem with the cross-sections quantum yields. As you can see for these examples shown here, CFC11 stratospheric species, identical, UTLS species like bromoform, nearly identical. Something's going on right at the top boundary, but who cares? There's no bromoform up there anyway. And then PAN, an important NOI reservoir in the troposphere, identical. We have some differences in one of the branches of formaldehyde, for example. We know there are a lot of choices with cross sections and quantum yields for formaldehyde, and we just happen to be using a different one lookup table than what was in TUVX. We'll just have to decide which one's the most appropriate. This is a pretty small change, though. Now, for the two most important photolysis species probably in the model, the JO2 and J ozone to their two different channels, we did the same thing, and they're almost identical. The ozone to OPPP is a little bit different at the top of the model, and we'll have to track down what's going on there. But this is really good agreement, and it didn't start out this way. We had a lot of iterations to get it to look like this. Now, if you don't use the same radiative transfer and for those 4 channels there, but use the radiative transfer from the lookup table and the radiative transfer from TUVX, it's still pretty good agreement. So meaning the radiative transfer between the two approaches was pretty similar. And there are some differences, and I just put question marks. These are things we'll follow up on, but it's great to see that the lookup table actually was doing a pretty good job with the radiative transfer, because I do believe the TUVX more so. All right, so that's photolysis. Looks like we have our cross sections of quantum yields in pretty good shape. Now let's talk about solar heating rates in WACM. And the two most important reactions in the MLT region for that is O2 and ozone. That's why I showed them in the previous slides. When they're blown apart, the energy can go into translational energy and can go into atomic or molecular internal energy. And in the MLT region, this energy isn't necessarily realized locally. It can be, these molecules can be transported to other latitudes. They can come back and react together, and they give off exothermic energy, and it's called chemical potential energy, and it can heat a different region of the atmosphere. So you have to count all the terms and all the reactions and all the energy in this model. And we merge the heating rates from our RTM around 60 kilometers to the WACM energy that's derived above from the photolysis and chemical potential energy routines. You can even lose energy in the system to air glow, where, and I'll show you, this is an example here. This is one reaction. Ozone's photolized less than 310 nanometers, forms O singlet D and O2 singlet delta. And all the way through it, in collisions and emissions, you're dissipating energy in the system. And this is what we have to keep track of in WACM. Okay. And if you do all that, you're going to get figures like this. And this was shown earlier, I guess yesterday, this figure. On the left is the heating rates calculated by the TUVX on the right. On the lookup table on the right is TUVX. The black line in this figure is what the QRS, solar heating rate, is for our TMG that CAM 6 uses and CAM 7 will use. The QRS total is the sum of all these other terms that are in the MLT region that we keep track of. And the thermal is important, obviously. That's probably the second most and third most important in this list here. The QCP here term is the chemical potential energy, and so that's when these reactions come back together and give off exothermic energy. And the sum of all this basically gives you the green line all the way up to the top. And if you look at the green line all the way up to the top between the two different curves, you can see it's very similar. So it looks like when we put in the TUVX, we had to rewrite the whole solar energy calculations done by the photolysis routine. And we did it right, and we got it done. Francis Vitt did a lot of work on this. So that's encouraging. All right, so just to kind of end this talk, we did run this one simulation with inline photolysis, and we ran it in specified dynamics mode. So this is SD-WACM nudged to MERIT-2 up to about 60 kilometers. And then above 60 kilometers is a free running model. And then the one on the right is when we had the lookup table in the radio transfer and for photolysis, and on the right is TUVX. And they're very similar. The seasonality looks pretty much the same. This is total column ozone, so it's really kind of focused on what the stratosphere is doing here. You can see in my arrows on the right, TUVX has some issues. The ozone depletion is a little bit too late. In the northern hemisphere, the tropics have too little of ozone. The southern hemisphere spring off 60 north has too high of ozone, and the depletion is not quite as deep in TUVX. However, I don't care. We finally have a model that runs. We have something that we can look at. We can debug this. We can figure out what's going on here. This is probably a few days' work at most. And the run on the lookup table is basically what the observations would give, because we've compared the lookup table to this year over and over and over again. So it's very encouraging. That's kind of looking at maybe more of a stratospheric focus. If you look at the troposphere is done. I mean, it looks the same pretty much in the lookup table at TUVX. And these are without any clouds. Both of these are clear sky simulations, so they're treated the same. So in general, I think we're really on a good trajectory here. And the next thing is going to be to work harder on getting the aerosols in the radio transfer for TUVX and then the clouds. We tried to do that for this talk, but for some reason it didn't work. We had a volcano, and there was no difference in the J's with and without the volcano, the aerosols in the radio transfer. So I don't know what we did wrong. Maybe it's a unit or something that when we're transferring the optical properties to the radio transfer of TUVX, it didn't work out. But generally, we're doing really well in cross sections and quantum yields. We probably still have a little bit more work to do. The photolysis heating looks good, and again, the next step is going to be to really take a look at the aerosols and clouds. And once we have that, I think it's going to be really interesting to see how the tropospheric chemistry responds. Are we going to have OH a little bit lower and have methane lifetime that's a little bit higher? I hope so. That's one area that I think we'll target right off the bat. So that's all I have today, and probably a couple of months out to have this done.
Very, very impressive. Yeah. So are there any questions? Let's see, somebody online has a question.
I do.
Yeah, go ahead, Rolando.
I want to know why the introduction of TUVX seems to degrade the simulation of ozone in the stratosphere. I mean, at least the photolysis rates that you showed are very similar for the things you compare. And not that one, the previous one. That one. Why is that really due to TUVX, or is it perhaps you have done short simulations and there is natural variability? What's going on there?
Well, it's specified dynamics, so we don't have to worry about the dynamics messing things up. I have a feeling it has to, part of it could be like the dimer chemistry might not be operating correctly. I didn't check the photolysis rate of the dimer. And
All right, so it could be details like that that are making a big difference.
yeah, I don't think it's not the species I showed you. They're the O2, the ozone.
Right.
Probably most of the CFCs are all correct, but there's something not quite right.
Right. Thanks.
Yeah. I mean, we have all the results. Yeah, probably within a day, I could figure out what's going on. I just haven't had time.
Okay, great. Other questions?
Yeah. So the TUV stops at the lambda alpha?
Yes, it does.
Okay.
Yeah. And then we have the photolysis of EUV from Stan Solomon's and a couple of sort of.
And what's the overhead for the computation?
Why did you have to ask that? Well, the key is, and I didn't talk about it, is we haven't worked on any optimization of TUVX. And so it's about a 15 to 20% additional runtime. But there are all kinds of ideas on how to speed that up. So I'm not too worried about that. We can get it down to 5 to 10%. I think it's a win-win because it's such an improvement in doing photolysis for the troposphere and stratosphere.
Rafa.
Thanks, Doug. Really nice development. Yesterday we had a talk on RTGMP. Is this TUVX being able to be coupled to the advanced P version of the redox transfer?
From yesterday? I don't see why not. That's the first I've heard of it. So, but whatever Cam 7 decides to put in, we'll use, and when we put the TUVX into that version of the model, we'll connect to it. So, yeah, I don't think there's going to be an issue.
Okay, thanks.
Can I just add to that? There's a PR open for the RTMGP, so we'll go in pretty soon, and we hope to turn it on as well.
Yeah, that's great.
Shouldn't. It shouldn't impact.
I don't think it will. No. If the bands have changed a little bit, because we'll take like for aerosols, what's in the aerosol bands of our RTMG, we then interpolate that to TUVX bands, but that can change, but that'll all be handled in the interface. I don't think that's going to be an issue.
Thank you very much. Our last speaker in the morning session, Lee. This one? No. Yeah, do we have Lee's talk?
If you go up to the drive, you might have to download it.
Disappear? I don't see it.
I think you have to go to the drive.
Oh, yeah, we can do that now. Should be here somewhere.
And then
Yeah, it is. Okay, I can download that.
Well, you're opening it in slides, not download.
I think you download it.
You see it now?
No, you did not download it. You just opened it in slides. Go back.
Well, that worked.
Yeah, I need to download it right here. Sure, just download it now. There we go. Okay. Just go to the download part. Save. Mistake earlier. There we go. Now it should be. We have it twice here now. Okay. Thanks. Thank you. I think it's easier to just use the arrows and the.
Thanks.
Okay, so go ahead. Hanni's talking about WCAMX recent developments.
Yep.
Thank you.
Thank you. Gizmo. So yeah, so this is just a collection of the recent developments. So you can see a lot of colleagues from many labs are involved. So I want to thank all of them. And to remind you, WACAMX is one of the atmosphere components in CESM, and it extends from the ground all the way to the upper thermosphere, and it builds upon CAM and the WACAM. And also it's a part of the CEMA and the geospace component there. So actually, most of the recent developments here are concerning the adaptation of the new dicore, spectral element dicore and AMPAS. I should mention that AMPAS here is mainly still at the WACAM stage. It has been a step toward WACAM-X, but not there yet. And in the grand scheme of things, this will be a part of our whole geospace modeling framework. And the WACAM-X is supposed to provide the underlying atmosphere for the whole geospace model, and it will be coupled with a MAGE model, the multi-scale atmosphere geospace environment model. And currently, we can do a one-way coupling. We can take forcing from the high latitude forcing from MAGE and drive WACAM-X, and then we have done a prototype study going back. It's file-based two-way coupling, but the MPI two-way coupling is something we need to work on. Another reminder, this is the kind of the main WACAM and the WACAM-X components. And just to point out that the red items are the things that we have been working on in last year or so, or 2 years. And the blue is what I mentioned earlier, the AMPAS development for WACAM. So a bit more detailed on the WACAM-X dynamical core. So this is based on the standard SE dicore that we're going to introduce in the new CESM3. And but in the thermosphere, the specific heats and gas constant and mean molecular weight, they are all variables, and they depend on the major species. Currently, the major species WACAM-X include O2, hydrogen, and N2. And so that need to be taken into consideration. So the new implementation developed by Peter is to have implement a very generalized formulation. And also it's dicore independent, or supposed to be dicore independent. So when we get to the point of adapting other dicores like AMPAS, that should be very convenient. I think Peter mentioned this yesterday, the major species or the thermodynamic active species is part of the transport by CESM. One thing we found that is that the new external pressure based pressure gradient formulation Peter talked yesterday tend to cause more instability for WACAM-X. We don't know exactly why, but for WACAM-X runs, we usually have to go back to the set it back to the pressure gradient formulation, at least for the high resolution runs. Seems to be quite dependent on that. And as in the other, the standard dicore temperature is used as a state variable in the energy equation, which is much a simpler formulation than the potential temperature for the thermosphere. And if we look at the thermosphere, one of the big things is the molecular viscosity and damping increases exponentially. So at about 200 kilometer, which is the F-region height, ionosphere F-region height, the diffusion coefficient is about 10 to the 6th. And when you get to the model top, it's about 10 to the 9th or 10. So that's it's it's very big, and also you can do a scale analysis, and you find that when you're at 200 kilometer, for waves less than with horizontal wavelengths less than 200 kilometer, its diffusion, its dissipating time is comparable to the buoyancy frequency. So, and then that number goes to 4,000 kilometer when you get to the top. So when you get to higher resolution, it's very critical to include the molecular viscosity and diffusion. And that was what is done now. It was not formulated in FV, but now it's included in the SE dicore. And the price you pay for doing that is because the horizontal diffusion is still treated as explicitly. So you do need to do a lot of subcycling, especially when you do high resolution, to keep the model stable. So again, Peter touched upon this yesterday. We have two kinds of diffusion in place, numerical damping. I think this is mainly on the physical side, is because even we're including the molecular diffusion, but if you look at the viscous scales, that's way smaller than the scale we can resolve. So to kind of bridge the diffusion process in between, you do need some artificial numerical scheme to do that. So the fourth order hyperdiffusion is included all the way. So you can see that here, even in the lower part is not zero. And then you ramp it up in the middle upper thermosphere, where you do need to kind of get the smaller scales in control to make the model stable. And then the second order, the Laplacian diffusion, that's 0 up to near the top, where you ramp it for the sponge light. And we have at least three coordinate systems currently in the model. The physics mesh lives on the cube sphere, and then for the ionosphere, we have this field line based geomagnetic coordinate, and where we solve the electrodynamics. And then in addition, the O+ transport for the F region ionosphere, that's still with solving things on the old landmount grid. So there's a need to kind of mapping things among this three coordinate systems. And so this is why there's this development for the regrading scheme, and it's ESM-based regrading scheme that maps fields back and forth among those coordinates. And that has been designed to be, again, dichromate independent. So when later we come to the, to MPAS, it should be pretty straightforward to use this same regrading scheme. I think Nick mentioned some of this, the experiments we have done using the new dicore. And I think we have tried all the different horizontal resolutions from NE16 to NE120. And for the vertical, we're just starting to test the new system with additional troposphere, stratosphere levels. And so there are some test runs. The others, we have run 2 model years for both the NE16 130 level, which is a quarter scale height in the vertical, and the same solar condition for the high resolution NE120 and 273 levels, which is 1/10 of a scale height vertical in the middle end. And apart from that, we have done for the high resolution, that's the nature run. We're going to talk a bit more tomorrow in our breakout session. Group. And in addition to the nature run, we have also done a storm study by coupling with the Gamera driving. Gamera is part of the MAGE I just mentioned, which is the magnetosphere MHD model that provides the high latitude forcing. And also we have run, using this configuration, run the Hamatonga simulation. And apart from that, we have also done some NE30 runs, short test runs, plus the Gamera coupling run, and also the NE60 testing the high resolution imaging. And this is just a quick show of some of the zonal wind structure, zonal mean zonal wind for June. From 3 runs, this is the FB dichlor with the parameterized gravity waves, and this is the NE16 130 level Wacom X, and this is the high resolution NE120. And again, this is June latitude and height, and these are both models use gravity wave parameterization. And this one take out all the parameterizations in the model, so it's all parameterized waves. But not surprisingly, you have a very large winter stratosphere wind shear there. I mean, jet there. Strong polar vortex. But what's interesting is that some of the features looks like for example, the dichlor, I mean the jet core structure. Latitude and high structure looks pretty reasonable compared to observations or the climatology and several other things. For example, the symmetry of the MLT wind reversal, both the strength and height seems to be better captured in the high resolution run. And actually, there are a few nice surprises from the nature run that we'll discuss more tomorrow. So some issues, it's not surprising that with such a large model, especially with the high resolution, there are some memory issues. I mean, for Cheyenne, we always have to run on this is for high resolution. We always have to run on the large memory nodes. I think NE62. We have to use a large memory node. Otherwise, we have to undersubscribe. And the ratio, we had to do that, but Francis found some magic treatment for that. And so now with the optimization, we're now able to run on derecho without having to undersubscribe, which is really good. And then the other thing is that on the more recent tags running on derecho, it has some stability issues, especially with the high resolution. And we show two plot here. This one is the NE120 run with the new tag, I think 132 or 33. And this is the older tag where we run both on Cheyenne and derecho, and it seems that they are stable. This is after 1 day starting from the same initial condition. You can see, other structures are actually quite comparable to mesoscale structures. This is vertical wind, by the way, and but you start to see development of very small scales in the southern hemisphere. Not sure why yet. The other issue is somehow data serving. We served a part of the simulation already on Globus as part of the CEMA project, but seems that after last November, the shutdown and the transition, and the connection point doesn't work anymore. Not sure why. I reported this, and still yesterday I got a request asking for access to the high-res run, and they got some authentication error, and I tried it, also get that same error, which was problem. And so this is a part of the MPAS adaptation, and MPAS, of course, is a non-hydrostatic dichlor, And it's a final volume, secret staggering, tree following. And this is led by Sudha Kamali. And she is have been running mostly at 100 kilometer resolution, 70 levels. This is again for Wacom. And she has done one model year runs and for all three die cores and comparing them. And actually it looks pretty reasonable. This is the again for June for the three models, all with the standard gravity wave parameterization. And actually, you know, the MPAS A, even the jet strength is quite reasonable. We haven't looked at. I'm not sure if Sude is online, but I'm not sure if she has looked at the breakup of the die core in September or October. It's too late, but just by looking at the June, it looks reasonable. So I think that's it. That's all the recent development that the question is on that. Right.
Great, thank you, honey. Open it up for questions. Do we have any questions online? See? So this was a free running model simulation, not.
This is a
specified.
free run. Yeah,
Yeah.
this is a free run. Yes.
Doug.
So for the case where you turned off all the gravity wave tuning and you went to high vertical or horizontal resolution, can you learn what's missing in forcings? Like, you know, can you help the gravity wave parameterizations like Wacom?
Yeah, yes, I think so, especially for, I haven't looked too much at the MLT and lower. I think maybe you can already learn something here. I mean, the caveat here is that still, it's, we're missing some forcing. So that as a result, you are not getting the strong enough jet reversal and or barely reversal at all in the winter hemisphere. But we already get the the jet structure and also the asymmetry looks pretty reasonable. And one thing we learned from there, actually we do for the lower part, we do learn something. One thing we learned there is that if we analyze the resolved gravity wave spectrum, we see that they have a clear asymmetry or anisotropy. With the preferred propagation direction, mostly toward the eastward direction, and that actually seems to be responsible for for the asymmetry in the wind reversal, and that may be something that need to be taken into consideration in the parameterization. The other thing we learned is really in the thermosphere, because in the thermosphere currently we don't have any gravity wave parameterization at all because of the linear scheme. It doesn't really apply there, and then we learned that with that result wave forcing, we're getting much better improved circulation and better composition in the thermosphere. And that's something we can really apply in future for thermosphere presentation.
Valerie?
Only the multi-reversal and free dynamical course, if you show with last year. So basically around in the meteor zone, so different strength of reversal related different numerical damping in the schemes, or what's your interpretation?
Yeah, I don't know. We haven't. I think Suda did some wave forcing analysis, and I can't remember. It's in the paper she submitted. I need to review that. I think there are some differences in the in the planetary wave forcing, and also I think the wave the gravity wave parameterization are exactly the same. Yeah, all this it's all out of box. So I don't think there's a major difference there. So Yeah, I don't know. I don't know.
Also, it's communication of submarine gravity wave physics with dynamical core, I mean, right?
Maybe, yeah, or maybe it's just, if we run 10 years, whether it's always, technology or just.
I see, I see.
Yeah, of course, I guess
I
it's
missed-
right.
what is the horizontal resolution?
In all this is, it's a roughly, this is FB 09, so it's, and this one is NE 30, and this one is 120, so it's all around 100 km horizontal resolution.
I think you go first, no?
As you mentioned, using an explicit solver for thermal conductivity and molecular diffusion is
Right.
quite expensive. Are you planning on using an implicit solver with MPAS? Or is that
Do
gonna
you?
be implicit?
Yeah, no, I don't have any plans. I mean, do you have a plan?
It might be something we want to look into because it's so.
Yeah. I remember yes, for the
10:36
high
a.m.
resolution run, we, like, the split number just for the diffusion, is near, for a physical time step of 5 minutes, the subcycling is like 180 or something.
Yeah, it's pretty
So
insane.
very, and it's a uniform, right? So you don't really need it lower down, but
I think there's a lot
yeah,
of
that
efficiency
can
we
be,
could gain.
that's right.
Yeah.
Do you already have experience with the deep atmosphere MPAS version?
No, this is still the standard, not the deep atmosphere, yeah.
Any other questions? I mean, we can go, we have a general discussion, but I think we're ready for the break unless somebody has anything they wanna bring up at the moment. Do you want to announce the seminar quickly or just, the seminar is 11?
Yeah, it starts at 11:10.
Okay.
The seminar. It's actually one of the EMWG presentations that were converted into a seminar, so it is actually part of the conference. So-
Yeah.
But I hear there's coffee cake out there, and coffee.
Okay, let's thank all the speakers again and start the seminar then. Mhm.